All right, so unit testing, there are different kinds of tests that you can write, different ways that we do testing. Unit testing is the kind of testing that programmers typically do. Sometimes you'll have a QA team that does some testing of your software, but they don't do the unit testing. That is the responsibility of the programmer. So let's learn how to do that. And I want to start with an example. So we just had a student introduction video from Chaz, and he wants to be a fighter pilot. Well, here is an example of possibly the most complex airplane ever made, one of the most complex ones for sure, the F-22 Raptor. So this is a very complex piece of machinery, and here is a little schematic about the F-22 Raptor. It's manufactured by Lockheed Martin and by Boeing. And if you just look at that, just think about how many parts do you think that airplane has? Of course, we're not going to count them. We don't know exactly, but it's probably millions of parts. It's many, many parts. And those parts connect together to make subsystems, and those subsystems work together to make different parts of the airplane function and work. It is a very complex piece of machinery. So let's just think about how we might assemble this. If Lockheed Martin assembled it from untested parts, if they just got all the parts from all the suppliers, just put them together and made an airplane that way, that would never work. With that many parts, with millions of parts, there is no way that every part would work. And so the only way, in fact, if we assembled it that way, by just putting all the parts together and then taking it out and trying to fly it, not only would it not work, but you probably would never be able to fix it. It would be so complex and so time consuming and expensive to fix it that probably your best bet at that point would be to just crush it down for scrap metal and start over. So it would be cheaper and easier to do that. And so of course they're not going to build the F-22 in that way. What they would do instead is they would test each part before they assembled it. So they would make sure that each part works individually. And then as they start to assemble parts together, they test those subcomponents. So as you get multiple parts together that fulfill a common function, you would test those parts and make sure that together they do the right thing. Then as you get multiple of those components consisting of multiple parts and you start hooking them together, you'd test those again. So you'd constantly be testing as you were building this. And so by the time you're done, you would have tested every individual part, every subsystem, every set of parts that work together, and you will have tested the whole thing as a whole. And you would have done that before you ever try to fly it, and then you're still going to go fly it and make sure it works and test it in the air. You're going to test all the weapon systems. You would thoroughly test it. And that is the only way that you would have any hope of making something that complex actually work. As we are doing this, if we find any parts that don't work, we would replace them or fix them as we go, because it would just be way too complicated to do that at the end. And what that would lead to is a working system. Now let's think about this in the context of programming. So there are two approaches to programming. We could take approach number one and say, I wrote all of the code, but when I tried to compile and run it, nothing seemed to work. Now just ask yourself, have you ever written code that way? Have you done that when in any of your prior classes or on any other project you've worked on? I'm going to guess that the answer to that question is yes, and then you're a little surprised that it doesn't work. Well, you shouldn't be surprised at all. You shouldn't expect it to work if you do it that way. If it's complex at all, you shouldn't expect it to work if you just write all the code and then get it to compile and then you wonder why it doesn't work. So what we should do instead is we should do the same thing that we do if we create an F-22 Raptor. We should write a little code, maybe a method or a small class, and then test it. If it doesn't work, we should fix it. If it does work, then write some more code and test that. And once we have these different units or these different classes and methods, and we know they work individually, then we start assembling them together into larger and larger parts of the whole program, and we test them to make sure that they work. And as we run into problems, we fix them as we go. One of the things that is interesting to know is that software is actually incredibly complex. If you think about how many lines of code there are in a small or medium-sized project, it can easily run into the millions. I've worked on projects that have had many hundreds of thousands and probably millions of lines of code. So similar in complexity to an F-22 Raptor. And you often are on a project with multiple teams writing code and integrating that together. And that is very complex. It's every bit as complex as a complex piece of machinery, like a fighter plane. And so really on a large complex piece of software, we don't have any hope of getting it right unless we're going to test as we go. So this is the approach we need to take, although sometimes we try to take this approach. We try to take approach number one and hope it works. I'm going to guess though that many of you have done all-nighters working on some project before because you tried this approach. You tried to build it all at once, all together, and found out that that wasn't working well. Okay, so that's what we need to learn how to do, is unit test our code and test larger and larger pieces as we assemble them together. So large programs consist of many smaller pieces. They consist of classes. Those classes consist of methods. We tend to put classes together in packages, and we need to test each of those pieces individually. When we test a small piece, we usually call that a unit, and the test we're testing it is a unit test. So usually the way we define a unit for unit testing is we define that as a class. So if a unit is a class, then a unit test is a test that tests the functionality of a class. Now a class will usually have multiple methods, so that means we're going to have multiple test methods to test that unit of code. All right, and then there are a lot of ways to categorize testing, but one of the common ways to categorize tests is by either unit testing, integration testing, and system testing. So unit testing is testing units or individual parts or components in isolation of all other parts. So testing them individually by themselves. That's unit testing. And that's what we're going to focus on in this class. And other types of testing you would typically learn about in a testing class. Integration testing, though, is testing different units that are supposed to work together. So if you think about your family map server, as you understand it, the design, we have multiple parts. We have model classes, we have DAO classes, we have service classes. Those are the ones you focused on mostly so far. We could test them individually as units, but they work together. And so testing that all those parts work together would be integration testing. And then when you have a whole system and you test it, equivalent to taking the F-22 Raptor out and flying it around and making sure it flies and moves right and that its weapon systems all work, that's system testing. And we really need to do all three kinds in software development. We are going to, in this class, focus on the unit testing aspects because that's typically what developers do, and often QA groups do the other testing. Okay, so just to reiterate that point because it's really important, when you leave here and you go to work as a software engineer, nobody else is going to write your unit tests for you. That's something you're going to do, and it's really part of doing your job. The job of a software engineer isn't just to write code, but to write code that works. And in my experience, untested code is broken code. If you write code that isn't tested, it doesn't work. If there's any complexity to it at all, if you haven't tested it, it doesn't work. And so that is going to be your responsibility to write unit tests for the code that you write. And then depending on the size of the organization and the type of organization, you may or may not have a QA group doing other levels of testing. If in a small startup company, you're probably doing all of it as a software engineer. And in a larger company, you likely have people who have based their career on, instead of building software, their career is based on breaking software. And they're going to focus on writing these tests where you'll do the unit testing. Okay, so are there any questions so far about what unit testing is and how that fits into a development process? So to summarize, just like we would build an F-22 Raptor, we are going to, when we're writing complex code, we're going to do it iteratively. So we will write some code, write some tests, write some more code, write some more tests. And we will do that by building up unit tests as we write our individual units that make up our program. So here's what unit tests do. They typically create objects, they create instances of the class that they're trying to test. They call methods on that object, and then they verify that the results they got back are correct. That's basically what a unit test does. And they will call them under all the different circumstances they can be called. So that means multiple unit tests, and verify that under all these different conditions under which a method can be called, the actual results we get are always what we expected. And if they're not, then we either have a bug in our code or our expectation was wrong. And either way, we need to correct something. We either need to correct our code or correct our expectation about what it should do. Another thing that's important is that unit tests are automated, so they can be run frequently. When I first started out in software development in the mid-90s, it was not very common to have automated unit tests. We didn't have good testing tools for that. And so what we usually would do instead is, first of all, if we could get away with it, we wouldn't write tests because we didn't like to. But if a manager made us write tests, then we would have to create some kind of a document. So we usually would do that in a spreadsheet. And we would describe how to set up the test, we'd describe what values to pass the method, how to call it, so it'd be a step-by-step process. And then there would be steps interspersed throughout that where they would say, now verify that you got this result. And often there would be some way to put a check mark by it that says that it worked, and then often you'd have to sign it and show it to somebody that you tested your code. Now, as you think about doing that, that doesn't sound very fun, does it? It doesn't sound probably like the reason you want to be a software engineer, if that's what you want to be. And so we didn't like to do that. Nobody really liked to do that. And so we tended not to do it unless we had to. And if somebody made us, then we would write that unit test plan. We would run it the one time we were required to, and probably never run it again unless somebody made us run it again. So that was definitely not very useful, not as useful as it could be. But now we have automated unit tests and automated frameworks and tools to make it easy to run those tests. And so it's not only more enjoyable to write them because you're writing code, but it's easy to run them because you push a button and they all run again. So as you make changes, it's really easy to run all of your tests and confirm that you didn't break anything. So because of that, we want our tests, our unit tests, to all be automated so we can run them all the time. So we can run them whenever we make a significant change and make sure that we haven't broken anything. When we get a bunch of tests together, a bunch of unit tests, and we can run them all together, we call that a regression test. And what that allows us to do, if we have enough tests, then we can confirm that as we make a change, we don't break anything. You've probably already had experiences in your prior classes where you had some code that was mostly done and it was working, and then you had to add another feature, another requirement to it, and you got that requirement working, but then you broke something else. Has anybody experienced that before? Raise your hand if you have, or give me a yes if you've experienced that. Yeah, it looks like quite a few of you have. So what you have experienced then, that's called regression. So what that means then is you have written code, and then you've written code later and broken code you'd written before, so your code regressed. Instead of getting better, it got worse. So that's regression. And we want to be able to test for that, and we can really only do that if we have automated tests. And so what we do is we're making changes, we keep running all these tests that we've written before, and if any of them fail, we know we regressed, we know we broke something, and then we go back and fix it. So this is really powerful, and it makes life so much better. When I started writing unit tests as a software developer, automated unit tests, and when that started to become more of a thing and we had tools to do it, my life got a lot better. I had a lot fewer sleepless nights, a lot fewer all-nighters, a lot fewer missed deadlines, because I was able to test as I went. So what these automated tests do is they notify you when you've introduced a bug, and they help you to create a much better system. The way it works is you have a test driver program that can run all of your unit tests. And it needs to be really easy to insert new tests into that driver. That should be almost trivial to get your driver to run a new test. And so then after running the tests, the test driver will tell you if everything worked, or if everything didn't work, it will give you a list of tests that failed. And I'm going to show you an example of that. So test drivers are now just built in to most development tools, and it's pretty easy to add tests to them and get results. And we'll see an example of that. There's a really popular framework for that, for unit tests, and a tool to make it easy, a test driver tool and framework called JUnit. And the way where this came from is a guy named Kent Beck wrote a tool. He wrote it for testing Java code, and he called it JUnit for Java unit, and it was for unit testing Java code. It was a standard way that you could write your tests, and if you wrote them in that standard way, his tool and his framework would recognize that the code that you wrote was a test, and it would run it. So you could write a bunch of tests, and that framework would recognize what all the tests were, and it would run them all. That was a really good idea, and so it wasn't just written for JUnit. It started, or for Java. It started out for Java, and then versions were created for other languages too. And so when we talk about kind of generic terms, when we talk about that framework, in the context of any programming language, we usually call it XUnit now, where you substitute your language for X. So there's JUnit, there's C++ unit or CPP unit, there's NetUnit for .NET, there's PyUnit for Python, and they all follow this same framework and methodology for testing originally created by Kent Beck. So that's what we're going to learn about, is how to do JUnit testing. And once you know how to do JUnit testing, you can write tests in basically any IDE that supports Java, and your tests will work. So there have been different versions of this framework. It started before Java had assertions. So assertions in Java are things that you can use. You learned about the @override assertion earlier, and that was a way to mark a method as being an override of some other method. You can use annotations to note a lot of things on your methods, and JUnit uses them to indicate which methods are test methods. But JUnit existed before annotations existed in the Java language, so we used to go by a naming convention of our methods. So earlier versions of JUnit, you had to follow a naming convention for your test methods in order for the framework to find them. Now you don't have to follow a naming convention anymore. You just mark your tests as being @test, and I'll show you examples of that. And that means that it's a test method that the framework should execute. We also have a way to execute or to specify that a method is a setup method, a method that is needed to get us ready to run our tests. And so we have two annotations for that. We have a before each and a before all annotation. If you write a method in a test class and you mark it as a @before each method, that means that test method will run before each test method in your class. Typically, your test classes will have multiple test methods in them, and any methods that are marked with @before each will run before each test method. So let's say we have test method 1 and test method 2. If we have a before each method, it will run, and then test method 1 would run, and then before each would run again, and then test method 2 would run. So that's the way that works. So that gives you a way to do any setup that you need to do for all of your tests, for each test. There's also a before all, which is another setup method, but it only executes once before all of the tests inside of a test class. So that's useful at times. It's not used as often as before each, but there are times when that's really useful. And then we have what we call teardown methods. These can be executed after each test to clean up. They're not as commonly used as before each, because what you find is sometimes the setup that you do before all of your tests also takes care of any cleanup needs, so you don't end up needing after each or after all methods. But sometimes you do, and so they're really useful to have. Remember on the previous slide, I told you the way unit testing works is you generally create instances of objects, you call methods on them, and then you confirm that you got the results that you expected. The way you do that confirming is with assertions. So there is an assertions class that has a whole bunch of static methods, and they all start with the word assert and then have other words after them. So for example, there is a assert true, an assert false, an assert equals, and several others, assert not null. And so that allows you to execute code, get some kind of a result, and then assert or check that the result that you got is what you expected. So you compare your actual results to results that you determined were expected when you wrote the test. And so these methods will confirm that the expected results match what they should, what you're saying they should match. And if they don't match, then you get something called an assertion error, which is how the framework knows that your test failed. And then it will notify you of that. And depending on how you're doing this, you might be doing this from a GUI tool like IntelliJ. And in that case, you would expect to be notified visually, and you are. But you can also run JUnit tests from the command line, and then you're notified with command line output. So there are different ways it can be integrated. So the next thing I want to do is show you that. I want to show an example of that. So I'll quickly show you that, and then we will take a break because I've been going for about an hour, and then we'll continue with unit testing after a break. So let me escape out of here. And we'll bring up our test project. So we have this code here. It's a pretty simple program called word extractor. And if you give it a long string, it will use some regular expressions. It's not too important that we go into the details of this code, but it will use some regular expressions to extract out the individual words, and then it will just add them to a list. So we end up getting and returning a list of words from the string. If you think about, well, how do you know if that works? You could write a bunch of tests to determine if it works. So pass in various strings with different features about them. For example, pass in a string that has one word and make sure that you get a list with exactly one word. Pass in a string with two words separated by a space and make sure that you see those two words when you call the method. So that's what you think about as you think about, well, what are the different ways that I can test this? What different strings should I pass in? And what results do I expect? So if we look over here, here is a JUnit test for that method. And it's a test class. It's got a before each. So the before each creates an instance of the class that we're testing and creates an array list that each test method can put its words in. And then we have a bunch of tests that test different possibilities. So for example, what would happen if we passed our word extractor an empty string? Would we get back an empty list? Would we get a list with no results in it? What would we get? And we should decide what we should get and then confirm in an assertion that that's what we do get. Okay, so that's how you build up these tests. Then we test with one short word like the word We write another one to test with a long word. And then you start writing, think about other possibilities. And what you're trying to think about is, what are possible ways that this could be wrong? If I write my code, what are some cases where maybe the code wasn't properly written so it doesn't handle them correctly? So if we look here, we have a whole bunch of different test methods, not a whole bunch, but we have several. And we can run them just by, there are a couple ways we can run them. We can right click on the class and say run the test, because JUnit is integrated into IntelliJ. So when I do that, it's going to run JUnit in the background and cause it to run all these tests. Or I can just click the little icon right here and it will run all the tests. Or I can run individual tests. I can just run one at a time, either by clicking on these or by clicking in the method and right clicking. So what I'm going to do is click right here to run all the tests. And that's what JUnit looks like in IntelliJ when it tells you all of your tests have passed. So you see the class name, you see each test method that it found, and a green check mark to tell you that they all passed. And if they didn't pass, you would see a different icon here. So you'd see a red X, and there's another one, there's a yellow icon that indicates something else went wrong with your test. So what you want is green check marks. And if you see those, then you know all of your tests passed. And notice how easy that is. I can run them again just by pushing the button. So if I make some changes to word extractor, it's really easy for me to make sure I didn't have a regression just by telling it to run all the tests. Okay, so I'm going to stop right there. We're going to take a 5-minute break. We will start up again at 2:05, so you can think about what I've said so far, and I'll take any questions that you have after the break at 2:10. Okay, I'm back. Are there any questions now that you've had time to think about what we've been talking about with unit testing? Kellen, go ahead.
So in a project, when we write the tests, like the positive tests and the negative tests, in the end, we still want when we run our tests, we want all green check marks, right? Whether they're positive or negative.
Yep, exactly. So what the negative tests would be testing is that the right thing happens when you don't take the happy path. So for example, you could test that you get a database access exception when you try to insert a row that already exists in the table.
Yeah.
Yep, exactly. Good point, that you should always get a green check mark even for a negative test case.
Thanks.
Okay, Dallin, you have a question?
Yeah, you might have addressed this at the beginning, but for the reading for the documentation for JUnit testing, is that in the book somewhere, or is it a separate book? Because on Canvas, it wasn't anything that I was familiar with that we have access to, I guess.
The reading, what do you mean when you say the reading for the documentation?
There was some there's some like pre-lecture reading on Canvas. There's like, and it just said JUnit. Let's see, where'd it go? Yeah, JUnit documentation section 1, 2.2, and 2.4.
Oh, okay.
I don't know if that was an old thing or.
Yeah, we probably should have put a link for that, but that would be the JUnit API documentation. Sorry, I didn't realize there wasn't a link there.
No problem.
Yeah, that's what we were intending for you to read, is documentation from the JUnit website.
Okay, perfect.
Okay.
Oh, okay, Caden just put it in the comments, so that's good, in the chat.
Okay, good.
Thank you.
Okay. Any other questions? All right, we'll carry on then and learn more about unit testing. Okay, so I already talked about this, how to run your unit tests from IntelliJ. Android Studio is basically the same. You right click or you click on the little icons on the left, and that will allow you to run them. So pretty easy to run. You can also run them from the command line. So what you need is a driver class whose main method would invoke this class. It would invoke the org.junit.runner.junit core class to run your tests. So a little bit more involved, but still not too hard. And that would be something you would do. Usually if you're working in a company and you have multiple developers, you'd have some kind of a tool that can run the unit tests on everybody's code as they're integrating their code together. So here is a command line that would allow you to do that. So once you write a test driver that invokes the JUnit core runner, then you would call it by first, you'd need to put everything on the class path that you need. So you'd need to put this JUnit Jupyter API jar on your class path. That is the JUnit framework and all of its classes. And then if you're testing database code, you'd have to have and it's a SQLite database, you'd have to have the SQLite JDBC driver, and any other classes that your code is dependent on, you'd have them here. And then you would invoke your class that has the main method in it. So not quite as simple as doing it from the command line or from the GUI tool, but still not that difficult. Okay, I've touched on a few of the annotations that make up the framework, but there are others. So let's just review those real quickly. So first of all, if you annotate a method with @test inside of a test class, inside of any class really, that says that method is a test method that can be invoked by JUnit. We talked about before each and after each. And those are methods that get executed before and after each test. You also have your before all and after all methods. And you even have a timeout method. So that will allow you to make sure that a test doesn't take too long. So if you put at timeout 5 on it, then the test will fail if it takes more than 5 seconds to run. Now, seconds are really long in computing, so we don't usually want to time out in seconds. We want to usually time out in something shorter than that. And so you can change the units to be something other than seconds by specifying another parameter. So you can do at timeout, give it a value, and then give it a unit. And then there are different time units. Milliseconds are the ones we're most likely to use. So those are just some of the annotations. There are others as well that you can find in the JUnit documentation, but that is a set of most of the annotations that you would need to write JUnit tests. Okay, I talked a little bit about using a tool like Maven or Gradle. When I showed you the code, I showed you that we were giving you the jar files that you would need. But if you're using Maven or Gradle, you would want to just do that with dependencies. So here's the dependency for a recent version of JUnit. It's probably updated since this slide was created, but it's still probably 5.5 something. And it's called JUnit Jupyter API. That's the latest version, what the latest versions of JUnit are called. So if you copy that into your POM, that would give you JUnit version 5 to run in a Maven project. And here is the entry you would need in your build.gradle file if you're using Gradle instead. Okay, there is a detailed example that is in my code examples. So that's available if you want it. I'm not going to go through it, but that would show you more examples of tests. So you really have a lot of examples of tests. You have the ones that we're giving you as part of your DAO assignment. You have the one I just showed you, and then you have this more detailed one that you can look at. I want to say a couple of things about Android testing, even though we haven't gotten there yet. I'm gonna go pretty quickly on this part, but after you learn about Android, you'll probably have questions about how to test it too, and it just makes sense to me to have all the testing information in one place. So these slides will make sense later, but with Android, or they'll make more sense later, but with Android, there are 2 types of unit tests you can run. You can run unit tests that don't require your code to be running on a device. So those tests can just run within the IDE. But then there are other tests you might want to write that only make sense if your code is actually deployed to a device. For this class, we're typically going to just deploy it to an emulator that's part of Android. And so instrumented unit tests run on the emulator or the actual phone. When we have you test your code, we're just going to have you write local unit tests, but you might want to refer back to this information later to remind yourself that there are 2 different kinds of tests for Android. One other thing that I'll point out since I brought up Android, you do not need to buy an Android device for this class. So with Android Studio, it has built-in emulators that will emulate different kinds of phones, and that's really all you need. In fact, I've been teaching this class for a few years, and I don't own an Android device. My phone is an iPhone. So you really don't need to go out and get one. If you were hoping this class was your excuse, I'm sorry, it's not. Okay, so this is just kind of more of what I just said. The last thing I want to talk about is I got a question earlier when I first started this lecture about testing databases. And so we're going to address that now. There are a few things to keep in mind when you're testing database code. First of all, you're going to have your database driver on the class path. And if you're writing database code and doing it in IntelliJ, that's just going to be natural that you would already have the database JDBC driver available. But if you're running it from the command line, you'd have to make it available. The big thing to think about that is kind of additional with database testing is, first of all, we want our tests to be independent of each other. We don't want to write a test in a way that you have to run them in a certain order. that test 1 makes some changes to the database that then test 2 expects to see. That's a bad idea. It makes for really brittle tests, and it makes it so you're going to have tests failing not because the code is bad, but because things are changing in the tests. We don't want order effects or anything like that to exist within our tests. So that means that we have to be careful, because database tests will typically change database data. So if you run a database test and it changes the data in your database, now that data is changed for the next test. And so we have to be careful how we do that. There are 2 main approaches to doing database testing and keeping our tests independent of each other. One is we can recreate the tables before each test. So you could do that in a before each method. Within a before each method, you could call some method that deletes all of your database tables and recreates them and repopulates them with whatever values you want to have in them for your tests. That might be reasonable for a small database without a lot of data and without a lot of tables. But if your database gets pretty complex, you're probably going to want to do option 2 here, which allows you, says to roll back the effects of each test when you're done, so they don't affect later tests. Remember, you can run code in a transaction, and then you can decide to roll the transaction back instead of committing it. If you do that, you can run your tests, but none of the tests actually commit changes in the database, so no later test will see a change that an earlier test made. And I'm going to show you example code of that way of doing it. So that is my other example here. So here is a database test class. So it creates an instance of a database object. It opens a connection. It creates some tables. Actually, this is the previous way. I thought I had written another one, but I'll explain how the other way would work. So this is the first way. So this has a method for creating tables. It populates the tables. Notice it runs before each test. And so we only have 1 test, but if it would work if we had multiple tests. And then after each test, it closes the connection and sets the database connection to null. Actually, as I look at this is kind of a combination of both ways, because when we close the connection, we're not committing the change. So if we have multiple tests here, we actually could change this to be just a before instead of a before each. And then it would be an example of the second way of doing it. Sorry if that's confusing. Let me clarify that. So this method creates and populates the database every time. And this method chooses not to commit every time after every test. So we've got really a combination of both ways of doing the testing in this one class. If I change this to just before, then it would set the database up once, and then each test would run, and after each test, we would close our connection and we would not commit. But then we'd have to have a before each method that would get a new connection for us. So we have a connection that's not null. Okay, so hopefully that wasn't confusing there. It's just the idea that you have to have some way that your tests are not leaving changes behind in the database when they're done, so other tests don't see those changes. Okay, are there any questions about database testing or anything else I've said with unit testing? No? All right, so that is really what you need for this assignment, for your DAO assignment. You need to implement those DAOs and test by writing tests kind of similar to what you see here. Caden, you have a question?
Yeah, so with Gradle and Maven, like, I haven't really done Java or IntelliJ before. And Gradle's just, they're both dependency managers. Is it like, should I just look up how to use that? Would that be easier in the long term, or doing things manually?
Yes, it would probably be easier. Um, and I tried to give you the information you need to get started with them in the database lecture. So if you refer back to the last 3
Okay.
slides there, there's some information there. Yeah, in the long run, that will save you time. The main thing that saves you is if you look at the list of jars that we're giving you for this assignment, it's quite a few. We've got all of these jars, but by just making one entry in your Maven pom.xml or your build.gradle file, those tools handle transitive dependencies. So by creating just a dependency for JUnit Jupyter API, the tool will pull all of the others in because they're needed. So that's one of the main benefits you get. Unfortunately, there are some challenges or some problems with the integration with those tools with IntelliJ. So you run into a couple of problems. And that's why I have that document that I mentioned. It's in the help section in the modules. And that will tell you what you need to do for any problems that you run into using those tools. But yes, in my opinion, it's worth it. Even though there are some integration challenges with the tools, it's still, I believe it's worth using them.
Okay, so so those slides should be enough at the end of the database lecture, or
Yeah.
do you suggest looking up other things?
Yeah, they should be. It's my
Okay.
intent that they are enough.